So now we turn to analyzing these fascinating equilibrium reactions. And again, we emphasize the fact that we're building the entire understanding of equilibrium chemistry on the back of the Gibbs free energy surface. So when we analyze these equilibrium reactions, we're going to be plotting the free energy of formation of the reactants on one axis and the Gibbs free energy of formation of products on the other. So our general expression of A plus B going to C plus D is now represented on that free energy surface by the fact that if we start with pure reactants, we move spontaneously down the curve driven by the release of Gibbs free energy, which means, as you know, for a spontaneous reaction, delta G must be less than 0. Also, if we start with pure products, we drive spontaneously down the Gibbs free energy surface in the other direction, but delta G is still less than 0 as we move down that curve until we hit the equilibrium position for which delta G is equal to 0. Now, we know that under standard conditions we can calculate that change in Gibbs free energy as the change in enthalpy for the reaction minus the temperature times the change in entropy for that reaction. And we know that we can calculate the release of Gibbs free energy for any reaction simply by calculating delta H and delta S for that reaction. But we want to emphasize that the delta G on this plot is for non-standard conditions. And we will see, as we discuss equilibrium chemistry, how we can actually calculate that delta G for non-standard conditions. That is, we can calculate delta G anywhere on this plot if we have the right equation. We don't have that yet, but we're going to build the case for equilibrium chemistry on the free energy surface, and then we're going to calculate exactly how we calculate delta G. Before we proceed, it's very interesting to recognize that equilibrium processes encompass a broad range of systems. One example is the reaction between calcium carbonate, which is limestone, and calcium oxide, which is called quicklime. This reaction is extremely important for the production of steel. The calcium oxide, or quicklime, is an important constituent in the formation of pure steel. But the other product of that is the carbon dioxide molecule that comes off in the gas phase as we heat the calcium carbonate. But let's look at an experiment where we have calcium oxide, quicklime, coexisting in solid form with calcium carbonate inside a bell jar. So let's suppose we have a lot of quicklime and a very small amount of calcium carbonate. But if we count the number of CO2 molecules that exist over those two solid materials, it turns out that the number of carbon dioxide molecules is completely independent of the relative amount of calcium oxide and calcium carbonate we have. So I could switch so we have a very small amount of calcium oxide and a large amount of calcium carbonate, and if I counted every single CO2 molecules in the gas phase of that bell jar, they'd be exactly the same. And that tells us something very important about when we're looking at an equilibrium, and that fact is that the equilibrium is independent of the amount of either a solid or a liquid. And the reason for that is that the escape of carbon dioxide from that solid and the combination of those two solids is determined by the binding strength between CO2 and the two solids, and as long as those two solids are present, that binding energy is the same independent of the amount of the solid that's present in the bell jar. Now, we can also look at very important equilibrium reactions between cations and anions in solution. And this turns out to be very important for biological systems. In this case, silver chloride, when we put it in water, breaks up into the silver cation and the chloride anion. And we always go back and draw the equilibrium, that is, the rate of the reaction in the forward direction and the reverse direction match. And we always want to remember to put reaction arrows indicating that the reaction is profoundly dynamic, moving species from left to right and right to left, but at the same rate so that their concentration remains fixed. So let's examine two other very important equilibrium processes. Let's look at the physical relationship between the liquid and gas phase water. And we know that if we heat water, we will form the gas. In fact, we can see that if we boil water on a stove. The gas phase water that comes off is evident as steam. But if we have a condition where we've closed off the vessel and we put heat into that mixture of water in the liquid phase and the gas phase, after we've warmed it to a certain temperature, we have a certain fraction of the water present in that sealed chamber in the gas phase and in the liquid phase. And that simply means that at that temperature, we're matching the number of water molecules jumping off the surface of the liquid with the number of gas phase molecules colliding with the surface and rejoining the liquid phase. This is very important for global climate because as we increase carbon dioxide and methane in the atmosphere, as we've seen, we trap more and more infrared radiation. And as we do that, we warm the surface temperature, particularly the surface temperature of the ocean. And as we do that, we're driving more and more water from the liquid phase in the ocean to the gas phase in the atmosphere. But the amount of energy required to liberate water from the liquid phase to the gas phase is very large. It's the heat of vaporization. And when we put more and more gas phase water into the atmosphere, that's the energy that produces the massive storms, the hurricanes, the tornadoes. And as we know, the number of hurricanes and tornadoes is increasing, and it's increasing because the energy available comes from the conversion of the gas phase water molecules back to the liquid phase. Now, we can also, again, remind ourselves that if we insert an acid into water, we form the cations and anions in solution. In particular, acetic acid creates the H3O plus cation and the acetate anion. But it's a very delicate balance between the production of the cation-anion pair and the reformation of the acid. And acids have this wonderful characteristic that they range over orders of magnitude in their desire to come apart when they're inserted into water. So a weak acid is one in which a very, very tiny fraction of the original acid actually dissociates into H3O plus, which is the acidic character of the solution. And yet strong acids, such as hydrochloric acid or sulfuric acid, dissociate almost completely to form H3O plus. So the strength of the acid is then extremely sensitive to the equilibrium between the formation of products and the reformation of reactants.